All right, in this review video, I'm going to review part of Unit 6 that I left out in my last video and Unit 7. Unit 6, we're still continuing to work on momentum, law of conservation of momentum, and the thing that I left out in my last video was the concept of impulse. So let me talk about that. Let me share my screen first. Okay, let's first review the units. In the last video, we discussed that momentum is basically P equals, P is the variable we use for momentum. Give me 1 second and I'm going to turn off this fan. No more background noise. Okay, the momentum, we use the variable P of an object depends on its mass and how fast it's moving, in other words, velocity and in which direction. So momentum, we discussed that the unit are kilogram for mass. For velocity, meters per second, so the units are kilogram, meter per second. Recall that mass is in kilogram, right? Mass, do not confuse mass with weight. Weight is a force, and the force, the unit is newtons. All right, mass is kilogram. And so if you were to go on planet Mars or any other planet, your mass wouldn't change unless you actually, your muscle or fat content of your body changed. But your weight will change, which depends on how strong the gravity is on that planet. Okay, now recall from last video, we discussed that force multiplied by, so let's say there's a collision, the force of the collision multiplied by the time over which the collision occurred, like the time for which the two things were colliding, equals the change. It results in the change in its momentum. It actually equals the change in its momentum. All right, now this side, the left side, force multiplied by time, we call that impulse. Remember, I is the variable for it, impulse. An impulse has the same value as the change in momentum. The units are different. Because impulse is F times delta T, the units are newtons for force times seconds. Newton seconds. For change in momentum, we've already discussed it's that. But the value is going to be the same. So if I give you one, you should know that the other one is going to have, if I gave you the change in momentum, you'll know what the force times delta T is. All right, that's all I wanted to cover, and that concludes Unit 6. All right, now I'm going to talk about the next unit, which is about work, energy, and power. Remember, we discussed that work and energy are two related concepts. All right, so whenever work is done on an object, some sort of an energy transformation occurs. Some form of energy can change it to another. The work is defined as this. It's the force on a body multiplied by the displacement d times the cosine of the angle between the two. So let's say you have a box, there's a force pulling it like this, and it's displaced horizontally, maybe, because it's pulled, let's say it's pulled on a table, then whatever the displacement is, let's say the box is here now, you multiply the two and you multiply it with the angle, the cosine of this angle theta. What that angle does is this. Let's say that this body was dragged. There are a bunch of other forces acting on it too, such as, I'm going to use a different marker for those. Weight, right? There's a force called the weight, F grav. And there's also a normal force acting, which is going to be smaller in this case. But anyways, those two forces, the normal force and the weight, are, notice, they are perpendicular to the direction in which the displacement happens, right? When that happens, then those two forces are not doing any work. So the condition for the force to do work is that the force has to be in the direction of displacement. So for example, according to physics, if I'm pushing hard, like with a big force on a wall, but there's no displacement involved, then the net work done on that wall is 0. Okay, the net work done. There are multiple forces, and you could calculate the, sometimes there may be multiple forces acting on a body. and you have to calculate the work done by each individual force, then you add them up. So let's look at an example. Let's say you have a block, maybe it's a bucket. All right, if the bucket is being pulled up, so there is some force pulling it up, F applied, the weight is opposing it. If I asked you to calculate the net work done, then you would do this. You would first calculate the work done by F. And if the displacement, let's say the displacement was 5 meters up, and the force, whatever the value was, then the work done would be that force. Notice how I'm using W. So it's better not to use W for weight, but to use F grav or FG. F grav or FG. All right. So now I'm using W for work done. Work done would be by the force, applied force would be that force times 5. And the units are the same as the units of energy. The work has unit, joules. You're going to do the same thing for F grav, except that F grav is in direction opposite to that. So it's going to have a negative work done because the cosine of the angle between them is 180 degrees. Here we had cosine of 0, which is 1. That's why I didn't even bother putting it. So anytime a force is in the direction of displacement, it does positive work. Anytime a force does direction 180 degrees relative to the displacement, such as F grav, then you simply get a negative 1 because of the cosine, except being cosine 180 degrees. So that's how you calculate the work done on an object. Now let's talk about law of conservation of energy. All right, so anytime anytime some sort of a force is doing work on a body, it can change one form of an energy into another. We pretty much focused on basically the work done by gravitational force on objects. So let's say that you have a block of wood which is sliding down some ramp, which is called an inclined plane. Let's say it starts from rest. So here, the initial velocity is 0. And it right here, it would have achieved its largest speed before it stops. But we're not going to include the part where it stops, because then another force kicks in, right? The stopping force. So we're not considering that. There are two forms of energy. Remember, kinetic energy is the energy associated with motion. Formula involves speed, half of mv squared. Potential energy is associated with position, in this case, height. So in the gravitational field, so it's mgh, h being this vertical height. To solve problems like these, all you have to realize is that up here, if it starts at rest, it has no k. K is 0. And you can calculate PE using formula. At the bottom, the height is 0, so PE is 0. And the KE is maximum. So as this block slides down, its potential energy converts into kinetic energy. So if you wanted to say, if I asked you to find the speed here, all you'll do is you'll set the potential energy initial at the top, initial, set that equal to kinetic energy, half of mv squared, at the bottom of the hill. And you can just get rid of these I and F once you know what you're talking about. And then just set up these formulas. You just put in the formula for mgh, and you'll see that if there's no friction involved, I didn't mean that. Go back. If there's friction involved, if there's no friction involved, then you simply set mgh equals half mv squared. Law of conservation of energy, mass cancels out. So mass doesn't really matter. It doesn't matter what's sliding down that ramp. You will still get the same speed using that formula. G, remember, is 9.8 meters per second squared on Earth. I will give the value of that in the formula sheet, please. Now, what if there is friction involved? Then you have to look at the more general form of law of conservation of energy called work energy theorem. In that case, we add the work done by friction or whatever that force, which we call a non-conservative force, is. So this is how it goes. It says that, let's say that the total energy. The mechanical energy, by the way, remember the mechanical energy of a body is Ke plus Te, kinetic plus. So I'll read this, Ke plus Te initial, plus whatever the work done that could generate different forms of energy like heat, light, or whatever, is work done by a non-conservative force will equal Ke final plus T final. Again, going back to RAM, in that case, the mass does not drop out because this term you have to calculate that or plug it in as FD cosine theta. So in that case, what you would do is, I asked you to find the speed at the bottom of the RAM. I would have to give you either frictional force or in which case you will put frictional force here, multiplied by displacement. That displacement would be this distance, not the height. Height will appear in potential energy formula, be that. So make sure you understand that which distance goes where. And then you simply plug it in. If you want some practice, go back to that test that you took on this. In a minute, I can look at that too, and then just solve problems like this to kind of remind yourself how to solve a problem like that. But that's basically all there is to work energy theorem. This is a more general form of law of conservation of energy, all right? As long as there's no outside, no other forces other than what we're considering here, then this will work. Okay, so I think we have covered this. Now the last concept is power. Power, P, is a variable. Tells you at what rate the work is being done, or maybe something is converting energy, like a light bulb converts electrical energy into heat and light. At what rate, like how many joules are being converted to another form of energy per second. So the formula is either work divided by time, or if you're thinking in terms of energy, you can say energy divided by time. So the units are joules per second, but we don't use per second because 1 joule per second is called watt. Just like on your light bulb, that tells you how much energy that bulb is changing, converting to heat and light per second. All right, so that's the unit of power. Work and energy are in joules, so W and E are in joules, remember? So there you go, that's all the units covered. So as far as I can tell, I think I've covered everything here. But as usual, like I said, don't restrict yourself to just this. Go back to that unit, open up unit 7 folder, which is, let me remind you that you'll find it in, I mentioned it in my last video where to find all that stuff. I mentioned it in class too. All right, we'll stop at this point. Now go ahead and just kind of maybe use the past test for extra practice or look over your worksheet.